All right, please welcome to the stage Mitchell. Mitchell is on our infrastructure team and is going to tell you a lot more about our infrastructure and data sets.
All right. Hi, everyone. I'm Mitchell. I'm an ML engineer at Comma, and I'm going to talk today about what it takes to build a data set with 1 million miles of driving. So the first question we should ask is, why do we care about this? Like, what's so important about the data sets? Well, you know, autonomy at Comma, our team is in the business of shipping neural nets that drive your car. And a very wise man once said that a neural net is nothing but a compressed version of your data set. In fact, I think we can be even a bit more explicit than that. The neural net is the data set. And if your data set's good, your neural net will also be good. And so, minus the bugs in the training stack that make it worse. So if we want to train the best driving models that we can, we need a good data set. So the second question we should ask is, why do we need 1 million miles? Like, why 1 million? Why not 1,000? And the answer to that is that Comma's data center has grown over time. From 2017, we had a little pile of servers. This is the oldest picture I could find on our Slack. To 2019, where our servers were in a garage, up to now, where we now have 15 racks of machines, about 200 servers, I believe, with something like a quarter of an exaflop. So we're getting up there. We're still a few orders of magnitude off the hyperscalers. But our compute has grown substantially over time, and that sort of presents us with a choice. We could train bigger models with all this extra compute. We could train on more data for longer, or we could do a bit of both. So how should we spend our compute to get the best results? Well, a lot of people have studied this question over the last 5 years or so, especially in the domain of language modeling, but also more recently for diffusion models. And what's been found, by and large, is that you want to do a bit of both. You want to train bigger models with bigger data sets. So you want to scale up both of them together. And you can kind of see this. This is an old chart from an old OpenAI paper. Every color line is a different size of model. Data set size on the x-axis. You can see over on the left side, our data sets are small. And the big models and the small models, they get about the same performance. The big models just aren't that much better. And then as we scale the data sets, as we go over to the right side of the chart where the data sets are really big, the big models keep getting better and better and better, and the small models kind of plateau off. So big models can take advantage of all this extra data, and they can improve substantially. But if we want to train bigger models and get that performance, we need big data sets. So that's what we're going to talk about. So the first step to getting a big data set is we have to collect some data. Harold talked a little bit about this. We're very fortunate that we have a lot of people out there driving with openpilot. So we currently see just shy of 7,000 daily active users, and we get, I think this is wrong, I think it's about 1,000 daily hours of driving uploaded. Now, of course, not everyone who is driving with openpilot is uploading that data. Some people opt out, some people just never really connect to Wi-Fi, and other people are driving on forks that aren't usable for training. But despite all that, of the roughly 30,000 devices that Comma has shipped in its lifetime, we have data from about 20,000 of those devices. So the majority of our users are uploading at least some data. We currently get this should be right. So about 1,000 hours of data per day out of the 10,000 hours that people are driving with openpilot. So we get a lot of data. We can see, not all users are uploading the same amount. The distribution sort of follows a power law. So some people are uploading a lot more than others, but that's okay. If we look at a breakdown of our data, we can see vehicle-wise, we've got a pretty good diversity across a couple hundred different platforms, 35 brands. Geographically, we're not doing quite as well. We can see we have data from about 70 to 75 countries, depending on how you count. but the overwhelming majority of it is still from the US. So we've got about 86% of our data is still from the US. Hopefully that'll become a bit more balanced over time as we continue to sell more devices internationally. So what data are we collecting exactly? If you've worked with openpilot, you probably know a bunch of this. When you're driving with openpilot, it's recording data in 1-minute chunks. We call these segments. And a segment has a couple files attached to it. We have 3 video files because there's 3 cameras on the device, so we have the video streams for each of those. We have a log file that contains all the messages being passed around inside of openpilot as it runs. And this tells us everything we need to know about the state of the vehicle, the device, the control stack, everything. And then we have a quantized log file that's about 20x smaller, so it might be just a couple hundred kilobytes. And this contains just the very most important messages that tell us, for example, whether data might be useful for training. So we record this data, and then we have to upload it. So when openpilot connects to Wi-Fi, like when you pull into your garage and park, openpilot starts uploading Q logs to Azure. So we receive these uploads, we spin through them, and we look for segments that we think might be useful for training. We mark these segments, and we request the device to upload them. So we're going to ask it to send the full segment along with all the video files and the full log file. So Athena D inside of openpilot receives these requests and starts uploading the full segment to our data center. And then our data center receives that data and copies it all into our distributed mini key value storage system where it's going to live for the long term. So at this point, we have a bunch of data. We've uploaded all of this raw data from our users, and now we have to make a data set out of it. So we have to do a couple things at this point. We need to decide how many segments are going to be in our data set, which segments we're going to use, and how we should split it into train and validation sets. So we'll go through each of these real quick. The first question, how many segments should we use? And you might ask, well, we have all this data, why not just train on all of it? Like, what's the point of not training on everything? And the answer is, we train models of several different sizes at comma. We have the biggest models, like the world models, that we're very interested in scaling to large sizes. And then we have some other models that are much smaller. And you saw from that chart earlier that generally the small models can't benefit as much from these large data sets. So you're just training on more data for longer and making your experiments all take longer for no real discernible benefit. So what we would really like is to have data sets of multiple different sizes. We might have a data set that's like 10,000 hours, one that's 50,000 hours, 100,000 hours, etc. So we'll have data set sizes spanning like a solid order of magnitude or so that we can use for different model sizes and architectures. So then if we're not going to use all of the segments, then how do we pick which ones to use? Well, there's a couple different ways that we could do this. The simplest is just, pick a random subsample. But we can do a little better than that. So you can see in this red shaded area here, remember this is the distribution of how many segments we have for all of our devices. So some devices have way more data than others, and that tends to have a lot of duplication. So people drive the same roads over and over again because they're commuting to and from work, for example. And so this red shaded area here from users with the most data, that may contain a lot of drives that are less useful or more redundant. And so maybe we just want to shade from or draw from the blue shaded area underneath, which contains the vast majority of the data anyways, and this gives us a little bit more of a uniform distribution across devices. Maybe we want to undersample US data. Like we saw earlier, the vast majority of our data is still from the US, and if we're only going to pick a subset, maybe we want to bias it a little bit more towards international data, just so we're getting a bit more balanced of a distribution geographically. Maybe we want to filter out engaged data. Like for some types of models, like the final driving model, we don't really want to train the driving model to imitate the behavior of previous openpilot versions. It sort of introduces a feedback loop, so that's not great. So at this point, we may want to remove the engaged data from some of our data sets. And then at this point, we may also want to run experiments with different types of distributions. So we may want to shift it towards, for example, more highway data, less highway data, more curves, more situations that the model really struggles with. This is the point at which we can shift the distribution a little bit in any way that we want to. So, okay, now we've decided what's going to be in our data set. We make some choices for all these questions, and now we have to decide how we're going to split between the train and validation sets. So the training set is everything that the model's going to see during training, and the validation set is what we're going to evaluate on to decide if the model is overfitting or if it's not learning properly. So normally what you would do is take like 10% of your data as your validation set, but there's a couple different ways that you can do this. The standard way in like an image data set would be, you just take 10% of your samples, that's your val set. But in our case, well, maybe we could think about just taking 10% of the frames out of the videos, marking those as the val set, but this is not really ideal. These frames are way too correlated. You can kind of see here, on the left is the first frame from a segment, and on the right is a frame 1 second later. It's a little hard to see with the contrast, but they look almost exactly the same. Like there's basically no difference between these frames. And so if one of them is in your train set and one of them is in your validation set, you're just training on test. So this is no good. This is leaking information into our test set, and that's going to make our models harder to evaluate. So we don't want to do this. These frames are too correlated in time. So another thing that we could think about doing is splitting by segments. So we take some entire segments and pulling those out and marking those as the val set. And this is definitely better. This is more like what you might see for, as standard practice for like time series data sets, where you pull out big chunks of time and mark those as part of your val set. But this still isn't as good as we would like, because you can see, for example, here, this is a road that was driven by the same driver several months apart. And you can see, again, they're basically identical, where the driver goes under this overpass and then makes a left-hand turn. And so if one of these is in our train set and the other is in our validation set, well, the model's learning some things about what the driver is going to do by looking at this data that's duplicated in our test set. And again, this is not what we want. So what we'll do instead is we'll split by device. We'll have some users be in the train set and other users be in the validation set. And this way we can ensure as much as possible that we're not getting any kind of duplication and that we're really splitting our data into clean train and val sets that have as little overlap as possible. So specifically, we take about 6% of devices, plus all of the employee devices. We put those in the val set. We put everything else in the train set. Employee devices are in the val set because we want our experience when we're driving around San Diego to be reflective of what someone might experience with openpilot when they pull it out of the box and use it for the first time. So we don't want the model to know all about our commutes. That really wouldn't be fair. So, okay, now we've decided what's going to be in our data set and how to do our train and val splits, and now we need to get the data ready for training. We need to process it a little bit. So what kind of processing is involved here exactly? What do we need to do to get the data ready for training? Well, the primary thing that we need to do is run our localizer. So localization in robotics refers to essentially figuring out where you are and which way you're pointing at every moment in time. So in our case, what we're going to do is take a segment and we're going to run a Kalman filter that takes in the GNSS, accelerometer, gyro, and some visual odometry from the camera streams and stitches this all together into a trajectory that recovers the position and orientation of the device on every frame of the video. And you can kind of see this visualized here. Again, a little hard to see because of the contrast, but there's a blue path that shows exactly where the vehicle is going to drive. So this is the output of the localizer. And this particular output is super critical. It's mission critical for us. It's required for all of the models that we train, for the world models, for the driving models, for everything. And so we need to run it on all of our data. This includes the very biggest data sets, because the world model in particular is the model that we're most interested in scaling, and we want to use the largest data sets for. So up to the very biggest data set sizes, we need to run the localizer. Then we also have some auxiliary outputs, I guess you could say. These are things like lane lines, the lead car, that's just the car in front of you, detecting any lane changes or turns that might happen during a segment. And these are things that tend to be a little bit less mission critical. Lane lines, for example, are only used for display purposes. We don't use them for any kind of control. They're just nice to show on the screen. Lead car, we currently use that in chill mode, but as experimental mode gets better, that's also likely to become a bit less important. And lane changes, same deal. As we move to the future and potentially start doing more work with navigation, lane changes may also become a bit less important. So these outputs are only used by the final driving model. The world model does not use any of these. It doesn't know about lane changes or lead cars or lane lines or any of that. And the final driving model is generally trained on a smaller data set because that model is smaller for a couple of reasons. We need to run it on device, but also there's a lot of factors that govern the scaling for that model beyond just making it bigger. And so making the model bigger is not generally the way that we find is easiest to improve that model. So because of this, the auxiliary outputs, we run them on less data, and they're a bit less important for us in autonomy. And so I won't focus quite as much on these outputs for the rest of the talk. So now we have our data set ready to go. It's all processed, and we have to actually serve it to the trainers. So what does that look like then? Well, so we've got all this data stored in mini key value. We actually have a couple of mini key value instances. You can kind of see the computers involved over on the right side here. We've got mini key value raw in red. This is the cluster that stores all of the raw data. That's the videos and the logs. And then we have the processed data stored in mini key value SSD, which is called that for historical reasons. That's over on the left side, and that's about 300 terabytes. So mini key value raw is about 3 petabytes. A mini key value SSD is about 1/10 of that and about half the bandwidth. So when we need to serve the data, this would be like a PyTorch dataset class that you're writing. We need to load the data out from mini key value. For the processed outputs, these are basically just stored as NumPy, like MPY or MPZ files. So either like a compressed zip or just dumped as raw NumPy, as raw bytes. Then the logs, if we need those, we can spin through those just using the log reader from OpenPilot, the same tools that are publicly available. And then we got the videos, which we need to decode. So we've sort of been talking around this up till this point, but the videos are H.265 files, they're HEVC, and we need to extract frames from these videos in order to train on them. So we can't do this in advance. When we decode the video, we're decompressing the frames about 100x. So on disk, the video file might be something like 70, 80 megabytes, but when we decompress it, it's going to be like 8 gigabytes. So we can't do this ahead of time. We need to do it on the fly. We just don't have enough storage space. So we need to decompress. We need it to be fast, or it'll be the bottleneck for all of this stuff. And we need to do it for a bunch of different things. We need to do it every time we train, and we also require the video frames for a bunch of the processing stages that we'll talk about in a sec. So how are we going to decode these frames then? Well, when I joined Comma back in 2020, we were using good old FFmpeg on CPU. And on a machine with like 24 cores, we were getting something like 400 frames a second of decode, which is pretty good. You're running lots of these in parallel, and that was enough performance for the time. But as our models get faster, we get more trainers, and we need more decode. That was no longer enough. So now we would like to move the decode off the CPU onto the GPU. Around 2022, we started getting computers in our data center with GPUs in them. And GPUs have dedicated decode hardware that can decode at like 1,000 to 2,000 frames per second on like a normal consumer GPU. And so we would like to do this. The problem at the time was that we just didn't have enough memory to both run the models and do the decode on the GPU at the same time. So we got these really tiny little like consumer GPUs. These are like, I think these are like $100 a piece at the time, maybe less. And they have almost the same decode performance as the larger GPUs that we train the models on. So we just stuck a bunch of these in all our machines and used these for decode. And that got us, like, again, 2,500-ish FPS per machine. But the problem with these little GPUs is, like, they take up a whole PCIe slot, and eventually you just want all of your slots in the machine to be for GPUs that are actually running the model, because that's kind of the primary workload. So eventually we want to kind of stop using these and just run the decode right on the GPU next to the model. So thanks to some slightly better memory management, we can just run everything on the same GPU. And now on a server with 8 GPUs in it, we might get decode on the order of like 15,000 frames per second. So that's not too bad. We've improved quite a bit. All right, that's pretty much everything that goes into creating a data set. And with the rest of the time that I have, I want to talk a bit about a case study of how our infrastructure has changed over time and how it's improved. I remember when I first joined Comma, as kind of a joke, I stuck a sign on the door of the research team that said Department of Magic. And I thought that was pretty funny at the time. But really, the research team is not the Department of Magic. It's the Department of Tools and Infrastructure. And everything we do is really focused on writing better tools and infrastructure. Because as a team of like 7 people on autonomy, like the only way that we can continue to improve these models and ship a better driving experience to all of you is to make the tools and infrastructure better and keep them simple. So this is going to be a bit of a case study of what that looks like in practice and how our stack has evolved over time. So I talked a bit about the localizer that we need to run. This computes the vehicle trajectory across a segment, and again, we use this for everything. But we need to run a couple of things first before we can run the localizer. So this is what our localizer pipeline looked like when I joined in 2020. Specifically, the things that are most important are that we need to run ORB features and we need to run a segnet. So what are those? Why do we need them? Well, again, the localizer is this Kalman filter. We're taking in GPS, gyro accelerometer, but those sensors on their own are not enough to give us the kind of accuracy we need for the vehicle trajectory. We also need information from the camera stream. So one easy way to get information from the camera stream is to use something like ORBS. ORBS are a classical CV technique where you find key points in a frame. Those are things like corners or edges or points that are easy to recognize. And you track how those key points move between one frame and the next. And this kind of tells you how the camera is moving with respect to the scene. So we can do this, and you can see this in this middle picture here. We're generating all of these red tracks that show how the key points are moving as we're moving through the scene. But the problem here is that we want to know, again, how we're moving with respect to the static background. And there's also all these other moving objects in this scene, like cars that are passing us. We've got a car in front of us, and there will be key points on these moving objects. And those key points really mess up our estimation. So we want to get rid of those. We want to filter those out. And the easiest way to do that is with a segnet. We have a semantic segmentation model that we trained using the comma pencil dataset. This tells us like which pixels are part of our car, which ones are part of the road, and which ones are part of other cars, etc. So we can use this to figure out which pixels are part of moving objects on the road and remove any tracks that get matched to those objects. So all of that is kind of a lot. So we can see kind of all of what's involved there. This was the state of the localizer stack in 2020. And then in 2021, we launched the Comma 3, which now has 2 forward-facing cameras instead of 1. And so that means that we need to run the ORB features and the segnet on 2 video streams instead of 1. And that means everything is twice as slow. So in 2021, it's, again, a little hard to see, but it took 85 minutes to run 1 minute of driving data through the pipeline. Now that's pretty horrible. Like if we do the math on that to figure out like how long it's going to take us, we had about 1,500 compute cores at the time. That number's for a single compute core, but even so, to run 1 million segments through the localizer would take 40 days. Now, not only is that completely out of the question, but it also means we can't run any more than 1 million segments. Like if we wanted to run 5 million segments, that would take months. So this isn't going to work. We need to speed this up. So what can we do? Well, the first thing we need to deal with is the segnet. The segnet on its own is taking 60 minutes. And a large part of that is because it was running on CPU at the time, like just using Onyx runtime. And so, like I said, around 2022, we started getting servers in our data center that had GPUs in them. And so first order of business was we need to run the segnet on the GPU. So step one was just move the decode over. We already talked about that. Then we want to run the segnet on the GPU as well. Onyx runtime has a GPU backend for NVIDIA cards that works great. But then we were running in a fairly memory-constrained environment at the time, and so we could only have a couple of model runners active at any given point. So that still wasn't great. So then we switched to Triton Inference server, where we can batch up a whole bunch of requests, send them to a server that's got a couple model runners in it, and get the requests back and write them out to disk. And this way we can have a lot more going on in parallel, and we get better performance. And then lastly, we can quantize the FE16. This one's a no-brainer. Like we were running in float 32. By using half precision, we can almost double our inference speed. So with all of that considered, we can go from about 60 minutes down to 4 minutes for the segnet. So that's a huge improvement already. And with that change, we're now down to 29 minutes to process 1 minute of driving data, which, again, that's a lot better, but it's still not good enough. We still need to improve things. So next up is the ORB features. The ORB features are taking 17 minutes now. So that's now about half of the total time to process a segment. So we need to deal with the ORB features somehow. So the ORB features have a few problems beyond just the fact that they're slow. They're running on CPU. We can see from the video here that there's a lot of incorrect matches. So this is cases where like a key point in one part of the image is incorrectly being matched to a key point somewhere else entirely. And this gives us all these outliers, all this garbage that we need to filter out somehow. So partly because of that, we need to generate a lot of tracks. So this image right here, I think we have maybe like 600 tracks per frame. And then they're tracked over multiple frames. So you'd be like several thousand tracks at any point in time. And partly because of that, the localizer is way slower than it would be otherwise, because now this Kalman filter has a few thousand additional inputs, and that just slows everything way down. So not only is the ORB features like really slow, but it's also making everything else slow. And not only that, but the segnet is only used in the localizer stack to filter out moving objects. So what this means is if we could somehow delete the ORB features, we would get rid of the segnet, we'd get rid of the ORBs, which are the slowest stage right now, and the localizer would be way faster. And now the problem is we can't delete the ORB features. We need some kind of visual odometry because otherwise the localizer just won't be accurate enough. But what if we could replace the ORB features with like an open source visual odometry model? Over the last 5 years, there's been a bunch of really good ones. Models like Lofter, Flowformer, Tapier, just to name a few. There's been a ton. And these models look great on paper. Like the demo videos are super compelling. You can see the points being tracked over time. The problem is when we take these models and we run them on our data, it's not very easy to see with these lighting conditions, but Lofter is like completely garbage in these low light conditions. Flowformer is like slightly better, but when you look at the tracks that are being output, they're still basically unusable. And the problem is these models just struggle in a lot of real-world conditions that we see in our data set. And you can kind of understand why when you look at the data sets that these models are trained on. Like the largest data sets for these models are like all synthetic. They're all generated with like a traditional graphics engine, like Unity or Unreal or something like that. Kubrick is one such data set that's quite large from Google. My personal favorite is flying chairs. I don't know if you can see it from there, but you can probably guess from the name what's in it. So those aren't great. And then even the data sets that are based on real data, like ScanNet and Kitty, Kitty is actually driving data. So that should be perfect, but it's all during the daytime. And it's also a fairly small data set. I believe it just contains like a few dozen hours of driving max. Might be even smaller than that. It's been a while since I looked at it. So these data sets are just not enough. And these models, because of that, really struggle in situations where we need them to work well. So if we're going to make this work, we're going to need to train our own model. And that sounds great, but where are we going to get the data? Like, we just looked at these data sets, and if we just train a model on those data sets, we're going to run into the same problem as all these other models. So we need a data set somehow. Where are we going to get it from? Well, the idea that we had was, what if we just train it to predict the orb features? Like, the orb features have all these problems, but most of these problems are actually fixed if you just have a model predicting the orb features instead of using the raw ones. And you'll see what I mean here. So basically, the setup that we want to do is we'll input like a pair of images that are just two adjacent frames from the video. And we'll ask the model, we're just showing a little patch of the image here, we're going to ask the model to predict whether or not there's a key point on each pixel. And then if there is a key point, we'll ask it to predict how that key point moved between the two images. So we're asking it how this point in the image moved to the next frame. And then using a loss function like Gaussian NLL or Laplacian NLL or something like that, we can also recover an uncertainty. So the model can tell us directly how confident it is about its motion prediction. And that's great because the localizer takes uncertainties for each of its inputs. And so we can feed those confidence outputs directly into the localizer and improve the localizer pretty substantially this way. So putting it all together, this is our neural orbs model. And we can see that right away, there's way fewer of these garbage features. There's fewer features overall because we just take the very highest confidence ones. So that means we're putting fewer of these features into the localizer. And the model runs about 4x faster than the old orb feature stage. So we've improved this a bunch. We get rid of the segment. We'll use the segment to train this model and remove all the orb features on moving objects. But then once we have that, we can throw away the segment, and we no longer need it for the localizer stack. And best of all, this change makes the localizer about 5x faster, which is crazy. Like this improves the entire pipeline just from this one change. So we can see this was the state of the localizer stack in 2024. We got rid of all of these parts that were here before. The localizer is down to 1 minute and 20 seconds. Neural orbs takes like 3 minutes and 20 seconds, and the total time is down to just over 5 minutes. We can clean things up a little bit further even. We have this log processing stage, which was just reading in the logs and writing out a bunch of intermediate outputs to disk. That's kind of silly. We can just spin through the logs as we need them, so we'll get rid of that. We've got frame index and frame times, which is just reading some metadata from the video streams. We can combine those into a single stage that just does all of the metadata that we need from the video and saves that. So putting all of that together, this is where we're at in 2025. We have one stage to get the frame metadata, one to get the visual odometry, and one to run the localizer. And the whole thing is done in 4 minutes and 50 seconds. So that's a big improvement. We're booking right along, and the total data center throughput across all of our servers now is just shy of 2,000 segments per minute. So what that means is we can now process about 1 million segments in 8.5 hours, which is great. Remember, we were at 40 days before to do 1 million segments. We're down to 8.5 hours now, which I think is like 110x improvement. So about 17x comes from all of the changes that we just discussed. And then the remaining 6x comes from just getting more servers over time and growing our data center. But of course, we're still not done. We can still make this faster, and we can have even bigger data sets. So there's at least another easy 2x speed up on the table. We can do the decoding inside the Triton server, because at this point, creating and destroying the decoder objects actually takes a pretty significant amount of time. So just by keeping the decoders around for longer, we can make it faster. We can use a faster runtime, like Onyx runtime GPU is not as fast as it could be. Torch compile is like almost 2x faster if memory serves. We can quantize to in date. That's another free speed up as long as we don't lose any accuracy. And then finally, we could potentially combine the neural orbs and localizer stages into one, since the localizer is the only thing in our stack that really requires these visual odometry outputs. So we could save writing them out to disk and reading them back in, and that saves probably another 10%. So if all of that sounds interesting to you, I'm repeating what's been said earlier, but Comma is hiring. If this part of the work sounds like fun, come work with us. Do the hiring challenge and help us build a 10 million mile data set to get the next scale up for our models. And that's all I got for you. Thank you.
Thank you so much. All right, we have time for a few questions for Mitchell. Any questions?
Great talk. How does the left side driving data affect the training?
So we explicitly detect left side driving data just based on geography, and then we can use that to have a model that predicts which side you're on, just to validate those. It doesn't affect things too much because in all cases, like the localizer that you're running is the same. So the model may need to know which side of the road you're supposed to be driving on, but all of the stages up till then are completely agnostic.
Hi there, another question.
Okay, so you send back like a really short like log for all the road segments, but do you like on that look for key features like hard braking, hard steering, stuff like that? Be like, hey, we probably want to get those road segments back.
Yes. So the uploading, we have some of that information in the queue logs that we can scan through if we want to. Currently, we don't prioritize uploads that have like hard braking or hard acceleration. Although we've talked about doing this, this may be something we do in the future. But we have quite a bit of that data in our full data set, and so we can choose if we want to train on more of that data or to train the model to predict that kind of thing. And so that we do a little bit of.
All right, we can maybe take one more question.
Yeah, it's a great talk. One question is, previous talk I talked a little bit about the change in the dramatic change recently in better engagement, higher percentage. Does that fundamentally change how you decide to choose segments that you want to keep?
Right now it doesn't, because the differences are small. Like we're seeing maybe a 5% increase in engage time, but potentially yes. If we're at the point aspirationally in the future where like 90% of all of our drives are engaged, at that point, we might want to start to pull more specifically from data where the human is driving, just for that reason.
All right, guys, Mitchell will also be available in the Q&A if you have any more burning questions about his talk, but we are going to keep it moving. Next up, we have Roba. So thank you, Mitchell.